Okay, in this series of videos, we're going to be looking at the relationship of our special right triangles, which is our 45, 45, 90, and our 30, 60, 90. We're going to be exploring where does that relationship come from, and then also how can we utilize it. However, before we can even jump into our special right triangles, we need to ensure that we feel comfortable using the Pythagorean theorem and leaving things in their radical form. So that's what we're going to do here to start. So for each of these, we are looking for our missing side here. It is always important when we are dealing with right triangles that the very first thing we do is identify our hypotenuse because we want to make sure that we are treating it as the hypotenuse. So we find our 90-degree angle, we draw across from it, and this is going to be our hypotenuse side. Now that's important because of the Pythagorean theorem, a squared plus b squared is equal to c squared. The c squared is the hypotenuse, so we want to make sure that we're putting it on the side by itself. Utilizing that here, that's going to give us 5 squared, which is one of our legs, plus x squared, which is our other leg, is equal to 9 squared. In order to get x by itself, the first thing I'm going to do is subtract that 5 squared to the other side, and then square root both sides. Now at this point, I could go ahead and use my calculator to do the inside. That's going to be 81 minus 25, which is 56. So 9 squared is 81, 5 squared is 25. That's that math I just did right there, which is going to give me x equals the square root of 56. Now, oftentimes we want to leave things in their most simplified radical form. So this is an irrational number because 56 is not a perfect square. However, we can break it down into other possible perfect squares. So what I always say to do is to try to come up with the perfect squares you know and determine if they go into this number. So our perfect squares are 1, which goes into everything. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And that's typically as far up as we'll go. We might see some other ones. So looking at these numbers, I don't think 25 or 9 is going to go into 56, but I could double check. Nope. I might try 16. Maybe 16 goes into it. And it didn't. That was 3.5. So instead I'm going to do 56 divided by 4. And you know what? That goes 14 times. So I can break this down to the square root of 4 and the square root of 14. So once again, I checked each of these to determine do they go into 56 evenly, because these are my perfect squares, and 4 was the largest one that went in evenly. The reason I like doing this is because now I can actually take the square root of 4. The square root of 4 is 2, and I can leave the square root of 14 as it is. So here's our final answer. Let's do one more and see how this one shakes out. Once again, the first thing I'm going to do is identify where my hypotenuse is. So I'm going to go across from my right angle and identify my hypotenuse. That means when I do my Pythagorean theorem, this one's going to be on the side by itself. So that leaves me with x squared plus 7 squared is equal to 9 squared. Go ahead and isolate. So x squared is equal to 9 squared minus 7 squared. So subtracting that 7 to the other side. And square root. So I'm getting x is equal to the square root of 81 minus 49. Once again, I could do that out to the side. I'm going to use my calculator to help me out really quickly. 81 minus 49. And that gives me 32. So I'm looking for the square root of 32. Once again, I know this is irrational because 32 is not on my list. So once again, my list of perfect squares are 1, 4, 9, 16, 25. And at 30, I might check, well, that's 36. 6 squared is equal to 36. So I know that this is not a perfect square. So I want to see which of these numbers goes into it. Definitely not the 36 because it's larger. 25 is not going to go into this. So I'm going to try 16. So 32 divided by 16. You know what? That worked. It's 2. That means I can break this down into the square root of 2 times the square root of 16. Once again, because 2 times 16 is equal to 32. Once again, this is useful because we can actually simplify the square root of 16. We know that the square root of 16 is 4. The remaining radical stays as it is. So once again, this is how we can utilize using Pythagorean theorem and leaving our answers in their most simplified radical form.